Hi, Iris.
Hi, I'm just going to step out, get a coffee and come back.
Okay. Okay, I'll do the same. Maybe I'll be back to the restroom. Start 2 minutes.
Hello, how are you?
Good. How are you?
Good.
It's nice weather now.
Yep. Do we have everybody? Was I last? I hope not.
We have one more. Actually, hi, Dr. Masood.
Hi, how are you doing?
Good. How are you?
Pretty good. Thank you.
Are you at school? Yes. No.
Okay. Good evening, everybody. So welcome to Kuo Wang's PhD defense. And before we get started, we have set up a breakout room for the committee members. So I'm going to assign Aris, Arif, and Brad to the room so we can meet in the room, and then we can come back here while everyone else can just stay here with Kuo while we wait. Is it okay?
Sounds good.
Okay, I believe I have to assign you. You cannot yourself go to the breakout room, right?
Yeah, you have to assign.
Okay, let me assign.
And I think then you will bring us back because we will not be able to come by ourselves, I think.
So I will have to bring you back, right?
Yeah.
Okay, assign here. I see. Arif, Brad, Aris. Okay. What happened? I think you can move yourself, right?
Yeah, I think that they're.
Okay. And I have to move myself. I don't know how I move myself.
I can probably move you.
Yeah, can you move me? I don't know how to assign myself to that. Other.
So I assigned you to the breakout room.
Hi, Cole.
Oh, hey, so
How are
long.
you doing?
Good.
Yeah,
Such a while, like 2 years since we saw.
yeah, that is right. Probably more than 2 years, I believe.
Wait, you're a postdoc right now, right?
Yeah, that's right. So in the same group, I'm working with Professor Allison.
I see. That's nice. Like the same research.
It's totally changed actually. So I'm working on the floating offshore wind turbine.
Oh, it's a turbine. I see.
Yeah, wind turbine.
I see. Nice. And you're gonna stay here until you finish a postdoc, like for like 1 or 2 years.
So yeah, so I started in 2020, July 2020,
I see.
and it's been around a little bit more than a year. I stayed as a postdoc, and if I get a job this year, probably in August, I'll be moving to somewhere else. Otherwise, I don't know.
Well, I guess you can still stay, right? If you don't get the job.
If Professor Allison is happy with that, I don't know.
I see. And are
Yeah.
you looking for a school in the West Coast or somewhere
Everywhere.
everywhere?
Yeah, everywhere, but except for very large cities.
Except for large cities.
Right. Mhm.
I see. But the schools like in the West Coast, they're all around like in the large
Large
city.
city. Yeah, so I'm avoiding those schools.
Ah, I see.
Mhm.
Yeah. Yeah, I'm already in Bloomington. Like it's only 15 minutes or an hour away. It's not that far.
Yeah. So how long have you been in Bloomington?
Just like 2 months.
2 months. Oh, so you got a new job 2 months ago then.
No, well, so I started like almost 2 years ago. I was working as
Oh,
a part-time
uh-huh.
in the company, and I just started like full-time 4 or 5 months ago.
Oh, I see. So you remotely changed to full-time and now you are commuting then.
Well, it's still in Bloomington, so and
Uh-huh.
also I don't have to go to the company. It's just they said we need to move back, but
I see.
not
Yeah.
everybody. Like very few people are going back. So most of them
Uh-huh.
are working remotely. I'm still staying here. I moved here,
Oh,
but
I see.
I
Yeah.
had to go to the office. But yeah,
Uh-huh.
previously I was just working remotely. I've never seen anybody in the office before.
Mhm. I see. There. Back. Okay. Good luck on your defense.
Thanks.
Mute. I don't know how, but okay, we are all back in the session now. So I think everyone knows Kuo here. If not, Kuo has been working in our center for right from the beginning of the center, right?
Right.
As we will all miss you, right? You're always there in a corner room, but nevertheless, you have to graduate and move on, and we are all here to hear your presentation today. So take over, Kuo.
Sure. Let me share my screen then. Can you see it?
Yeah. Yes.
Well, welcome again to my final defense. And my name is Kuo Cheng. Dr. Kesh is my supervisor. And thanks to Dr. Masood, Dr. Shrenowas, and Dr. Sutton to be my committee members. Today's talk is going to be my PhD dissertation, and it's on FEA-based simulation of breast deformation in real time using artificial neural network. Here are the publications throughout my PhD career. And here is going to be our agenda for today. I'm going to introduce my research first, and then I will do like a review of the state of art. There are going to be three main parts of the research. In part one, I will introduce like how we build a computation model for breast deformation and the neural network model to learn the computation model. In part two, I'm going to show you the validation results of the breast deformation simulation. And in part three, I'm going to show you an AR application we developed of the deformation simulation. The motivation of the research is the breast cancer is the most common cancer among women, and World Health Organization estimated age standardized incidence rate of 84.9 per 100K in 2018 in the US. Patient takes MRI scans at a specific posture before treatment, which is different from the position during treatment, and that causes a shift of tumor, which makes it hard to precisely locate the tumor. So there are a few problems with the current research. First, there's not enough research focused on predicting patients' tumor location and breast deformation with different postures. And there's limited work to study how the structure of the breast affects the breast deformation. Traditionally, simulations are done offline, which does not provide real-time breast positions and tumor location prediction in the operating room. Even though there is like the problem was not well studied, I still listed some of the papers to show you the relevant research. In 2008, a research group constructed a neural network for liver deformation prediction. They formulated the contact problem by first estimating the force and then deform the tumor, which is not physically accurate because the force itself is estimated. And you can see the results from here. In 2012, a research group published their paper for breast deformation simulation that includes skin depth. And they found that the results were more accurate when we include the skin depth. In 2013, a research group modeled the deformation of the breast due to gravity with a spring damper model. For those of you who have a computer graphics background, spring damper is easy to simulate and it is pretty fast. However, it does not represent a correct physics of the deformation. So we usually don't treat it as accurate simulation. In 2017, a research group proposed boundary element method. So boundary element method is a way to numerically calculate like partial differential equations. In general, it works well when the surface to volume ratio is small. In 2017, a research group built a computation model on plate compression and developed two tree-based ensembled method for deformation prediction. And they are extreme randomized trees and random forests. In 2018, a research group used machine learning technique to learn deformation of breast conserving surgery, and they found the results to be relatively accurate. So the overall objective of our research is to build real-time accurate simulation of breast deformation. And based on the overall objective, we have a few bullet points listed over here. We want to use finite element method to solve breast deformation and tumor location under different scenarios related to the position of the patient. And we want to build a neural network architecture to learn the deformation as well as tumor location. We want to develop a virtual simulator that is capable of showing breast deformation and tumor position in real time. And we want to validate the accuracy of the deformation with a breast phantom. Now let's take a look at the part 1 of this research. Here is a general description of our method. We took a patient's data and did some preparation of the data. We generated tetrahedral mesh so that we can use for finite element analysis. We then built neural networks based on the training scenarios from the finite element. And we finally constructed a simulator that can be interacted with the user. So here are some of the topics I'm going to cover on this part. I will talk about data preparation and deformation computation. In deformation computation, there is finite element and neural network model. I will finally show you the simulator we constructed. Just to give you a better idea, here are some of the standard patients' postures. Now let's take a look at data preparation part. Our data source for the breast model is from this paper. The authors used 3D MRI scans on patients, and each scan has 240 slices and saved as DICOM format. Each slice has 256 by 256 pixels. The authors generated a 3D breast mask, and they used k-means cluster method to segment the breast into skin, fat, and fibroglandular tissue. The left part of each of this image is the original data we got from the paper. And as you can see, they're kind of messy, so we need to do some pre-processing. For skin mesh, we used Taubman filter, and we deleted nipple so that it won't affect later mesh generation. For fibroglandular tissue, we deleted all noisy surrounding parts, and we deleted some parts belong to vein. We used the Taubman filter to smooth the mesh, and we did some point decimation to reduce the number of points. We also remeshed for the holes on the surface, and we also did some manual intervention. For tumor, we used a Taubman filter, and we did some manual intervention. And as you can see, the right part are the results for these mesh.
What does manual intervention mean then?
So if we just use like Taubman filter to smooth the surface of the mesh, sometimes you can see like it's not that good, so that we have to manually delete some of the points, or there are some there are like softwares we can use to smooth it. For example, on this specific part, I can just use a brush to smooth the mesh.
Okay, and so is the tumor itself smooth, or do you think that the mechanical properties of how the tumor is interacting with the surrounding tissue is more of a smooth feature? Or is there a physical reason why you think we should smooth and the structure is not as jagged as what you got out of your direct segmentation?
Well, so if you look at this tumor on the left part over here, if we do a finite element, or if we want to generate a mesh for the FEA, the mesh, like that step will fail because like the part itself is pretty jagged, and also, yeah.
Okay, that makes sense. So it's the complexity of the mesh generation that's limited. So if you had infinite capabilities of meshing and solving and computation was an issue, do you think you would get a more accurate result? Or I guess I'm just trying to get your feeling as to whether the smoothing is important here, or if it still is a accurate representation of the tumor?
Well, I guess that's probably not a problem of computation power. I mean, if the mesh is not smooth, the algorithm will fail when they check the quality of the mesh. So it will stop before even like processing into mesh.
Okay.
It will just stop there.
And so it's related to the tessellation being invalid in some way from the original mask. Okay.
Yep.
Okay. All right. Yep.
Thanks for the question. So, well, since I talked about Taubman filter, I just put one slide here to explain. Taubman filter is an improvement of Gaussian filter. And I mean, Gaussian filter is very commonly used, and it has a problem of shrinking as the iteration increases. And in order to get good results, we need a large number of iterations for Gaussian filter. Taubman filter solves the problem by adding an expansion step after each iteration. So the volume of the mesh pretty much keeps similar. Finite element uses mesh to solve the partial differential equation. And for 3D data types, there are a few mesh types that are commonly used, like tetrahedral mesh, pyramids, triangular prism, and tetrahedrons, hexahedrons. We chose to use tetrahedrons because it's the simplest 3D mesh type. It is faster than other mesh, and it is like it can represent very complex shapes. And in fact, most of the surgery simulations are using tetrahedral mesh. There are a few metrics we can use to describe the mesh quality. Shape factor is the ratio of element volume and optimal element volume. In our case, the optimal element is the regular tetrahedral mesh. And the face corner angle is the angle between the edges of a surface in a tetrahedral element. And the aspect ratio is the ratio between the longest and the shortest edge of an element. In reality, when the model is complicated, it is very hard to guarantee all elements are in good quality. Here is our generated mesh. This is the breast structure. It is pretty complex, and researchers usually separate breast into skin, fat, and fibroglandular tissue. Sometimes there may be a tumor. For fat, skin, and glandular tissues, we modeled them with hyperelastic material, and the tumor is modeled with elastic material. All of those values are extracted from relevant papers. Since there are multiple materials, we need to embed those information in our simulation. For us, we used skin mesh for simulation, and we found a corresponding mesh for fat, tumor, and fibroglandular tissue in the skin mesh. Naively, we have to search each tetrahedron in different parts and find where tetrahedrons are in the skin. We speed up this part by using a grid search. We separate the entire searching domain into a 10 by 10 grid, and we find which grid the tetrahedron belong to first, and then go through each tetrahedron in that grid. Just to give you an idea, we probably have to use like 90 hours to find the fibroglandular tissue tetrahedrons. But finally, by using the research, we can just use, it only takes us like 10 minutes. And here is our assignment of the mesh. Now let's take a look at the deformation computation part. So FE simulation discretizes the deformation domain and solves the partial differential equation that discretizes the deformation. And FE can be separated into linear and nonlinear formulation. It can also be separated into static and dynamics formulation. Nonlinear finite element deals with large deformation and nonlinear material properties, and that's why we chose to use nonlinear finite element. Here is our boundary conditions of the FEA. The back of the breast is treated as pectoral muscle, and they're fixed in all directions. We started with 5 degrees and go up to 360 degrees with an interval of 5 degrees. And for each angle, we also generated the fibroglandular tissue over fat volume tissue ratio. And the reason we need to use this is we want to describe the structure of the breast. And as I have shown you before, the structure of the breast is pretty complex. And other research groups found that the fibroglandular tissue and fat takes the most amount of volume. And we can use the ratio of these two to represent a feature of the breast structure. So now we are pretty much done until finite element analysis. We need to continue to the neural network construction. Here is just a basic review of the machine learning formulation. Machine learning is used for 2 types of problems, like classification, which is to categorize one thing into a specific category, and the other is to predict a value based on the input, which is called a regression problem. Let's use L to describe the expectation of the error. X is the input data, Y is the ground truth. F is a function that used to differentiate between different machine learning techniques, and rho is the error. So we are trying to minimize the error between the predicted value F and the ground truth Y. For us, we have 3D data set. So we want to minimize the error between the corresponding points displacement. And since each displacement has X, Y, and Z, that's why we have X, Y, and Z over here. Yeah, I've already mentioned about F. And we chose neural networks as our machine learning technique because most of the papers I reviewed using neural networks. And other machine learning techniques explored before are radial basis function network, gradient boosting regression, and multi-output regression. Here is another review of the functions in neural network. So Z of L is the neuron values at L layer. It is a linear combination of the neurons from previous layer and a bias value at current layer. We need to add some nonlinearity, so that's why we have a sigma function. And for us, we chose ReLU as the sigma function. It is the max between 0 and the input X. The output U is also a linear combination of the previous layer neuron values and also the bias. So let me just show you some neural network structures from previous paper. So in this paper, the authors used 2 hidden layers, but they didn't mention the number of neurons in their paper. For the second paper, the researchers experimented the accuracy of using 1 hidden layer with different number of neurons, and it varies from like 20 to 300. This paper the third paper used 60 hidden layers. The fourth paper used 1 hidden layer with 4 neurons. So as you can see, like most of the papers are using like 1 to 2 hidden layers. Other than this paper, which use like 60 hidden layers. That's why we want to start with a shallow neural network. So this is our neural network. The input is a vector of 4. X, Y, Z is the direction of gravity. The ratio is the volume ratio between fibroglandular tissue and fat. And we trained 2 neural networks, one for breast deformation and the other for the tumor center location. For breast deformation, there are 2 hidden layers, and each layer has 60 neurons. For tumor location, there is 1 hidden layer with 20 neurons. The output is the displacement of either the point, like the displacement of each point, or the displacement of the center of tumor. Let's look at some of the results. The training error for tumor is 0.046, and the validation for tumor is 0.05. The training error for breast surface nodal displacement error is 0.013, and the validation error is 0.014. To give you more details, we used like 80% of our data set as training data and 20% of our data set as validation data. The result is bad when the training area is large and the validation area is also large. That usually indicates it's underfitting, which means the network is not complex enough to describe the current problem. And another type of bad result is when the training area is small and the validation area is large, and that usually means it's overfitting. It learns specifically for the training data, but it's not able to give good accuracy for like a general like validation data. So for us, since both of the accuracy are pretty small, and both of the error are pretty small and their accuracy are relatively close, that's why we think it's pretty good result. Here is a color map of the breast deformation. So as you can see, as the patient is getting up, there is more deformation presented. The top 2 for the fibroglandular tissue at the ratio at 0.33, and the last one is for the ratio at 0.66. Here is another view for a different anatomical plane. The same trend occurs as the patient is moving, moving more. You can see more deformations. And here is the results of the tumor. This part is for this deformation, and this part is for this deformation. So here is our simulator. So from the interface, you can see we can adjust the tumor size, and we can enter a fibroglandular over fat volume ratio. We can choose which anatomical plane we want the patient to go against, and also we can give a specific angle. After submitting, we can get a reconfiguration of the breast shape. Here is a demo of it. So now I'm using a transverse plane, and yeah, so I'm adjusting angles. And after submitting, you can see the change of shape. Now I change to sagittal plane. And you can also see the deformation when the angle changes. And now I change to a different glandular ratio. And you can see there's little like variations of the shape. Now let's continue with part 2 of the research. In this part, we want to further study the accuracy of our simulation. As collecting data from real patients is pretty hard at this time, we decided to use a breast phantom. And this breast phantom is proven to be relatively accurate, model that can mimic the breast. So we need to estimate material property, and we need to construct an FDA model. We also need to construct like neural networks to learn the breast deformation and tumor location. With like the whole approach is similar to what we have done for part 1. This is a more detailed description. Here is our breast model. We put into like an MRI scanner, and we put it into different angles. We collected the MRI scans and did 3D reconstruction. And also we need to register between different positions of the breast. We constructed the tetrahedral mesh, and we used an iterative approach to find the material properties. Just a notice, like this approach was not created by us, like it was created from a different paper. We just applied to this problem. And we built neural network, we constructed finite element analysis based on the mesh. And also we constructed neural networks. And finally, we did some validations, and I will show you in a later presentation. Here is our data collection. We used a 3T Siemens MRI scanner, and there are 20 channels in the head coil, and we put 3 markers here for registration purpose. Here is an example of one MRI scan or one slice of the MRI scan. We use T2 weighted MRI sequence because in this case, we can visualize tumor easier than like, here's another one, T1. And we did 3D reconstruction of the breast from the MRI images. We also segmented breast into tumor and skin, like manually. So here we don't have like fibroglandular tissue, so really we can't validate the structure of the breast, but still we can see like, we can get a sense of how well we simulate. There are 19 tumors in this data set, and we took one tumor for our experiment purpose. Here is our boundary conditions, and we still fix the back of the breast because they're like treated as pectoral muscle. This is the material estimation part. We use neo-Hookean materials, and we treat entire breast as a homogeneous material. So we start by finding the corresponding points between 2 nipples at different postures, and we initialize like a value of the material. We start the FEA and calculate the error between the nipple. If the error is small, then we say we find the best material property. Otherwise, we will guess the next value. And this entire optimization part is use BFGS. Now let's just look at some of the results. So I said we were using nipple to estimate the material property. So I actually draw an entire breast air distribution. And as you can see, like most of the air are between like 2.92 millimeters to like below 5 millimeters. And as a result, the average is 4.93. So this air is quite close to the paper we cited. So we just take this air, we just take this as the best material property we can find currently and continue with our simulation. Here is our training, testing, and validation data set. For training and testing, we started from 0 degree and go up until 360 degree with 15 degree apart. And for validation set, we start from 5 degree and go up until 350 degree with like 15 degree apart. And here is the result. For tumor air, the training air is 0.219. The testing is 0.269. Oh, those are all in millimeters. And for validation is 0.176. Just as a notice, the first three we're comparing neural network with the FEA model. The last one, we took the MR image at 50 degrees and we compared the neural network with the MRI data. And we found the air for tumor is 3.65 millimeters. For breast deformation air, the training area is 0.107. The testing area is 0.124. The validation area is 0.192. And also, finally, when we compare our neural network with the MRI data, the area is 2.69 millimeters.
Can I ask a question? I don't understand the table very much. So the first 3 rows are just simulation, right? And the last row is the only one with the MRI data?
Correct.
Okay. I thought you took lots of angles. Is that not what the last page said? The last page was just laying out the...
Yes. So all of those are for neural network part.
Okay, for the simulation part. Okay.
Yeah, all of those are generated from finite elements.
Okay. So how many angles did you take in the MRI data set? Just the 50 degrees?
In the
0?
MRI. Well, sorry, I actually don't remember on the top
Okay,
of my head. I think
fine.
probably 4 or 5. Yeah.
Oh, okay. All right. Yeah, and it does take longer. You can't take all of them with MRI. So it takes time to get each one. Yep. So
Yeah, and also we have to segment the breast. It takes a very
manual
long
segmentation too. Yeah.
And also like the data is very messy. Like you won't be able to use it directly. So
yeah. And then displacement errors on a tumor. How are those figured? Are those center of mass to center of mass or?
right, it is the displacement of the center of mass.
Okay, displacement of center mass. Okay.
Yeah, and actually I have a comparison here. This paper, they use the same model. But they use finite elements. They compare the finite element with the MRI image. And they call it lesion, I guess, but it's actually tumor in our case. Like they said it's a little under like 2 millimeters. And for breast deformation, they also took from different angles. And they said is between 2.499 to 3.817. So like our area is quite close. Yeah, that's why we further extend their research by using neural network. So it can be understandable, like it's a little larger. And also I did a visualization of this. So these are at 2 different angles. This is at 25 degree and this is at 50 degree. The left part, the transparent breast is the initial breast shape, and the right one is the one after neural network. And you can see the ground truth, like these two are kind of overlaying like on top of each other. now let's just take a look at the AR application we developed. So we have an Android tablet for the AR part, and for the server part, we just use a desktop. So for the Android, the AR part, we used Unity and Vuforia as our software development library. And for the neural network, we use Python and TensorFlow in desktop. And
before proceeding, can you say the motivation for what this AR tool was created? Why is it useful and for whom is it useful?
I see. Yeah, we want, I mean, in order for the user to use, like a doctor to use it in a clinical room, like we can't really bring we don't want them to just look at a desktop and look at the 2D images on the desktop and then compare. We want to, if we have like an AR app, we can overlay the breast on the actual patient. So like the doctor can actually get an idea of how it looks like on the patient. Is that enough or?
Yes.
Yes. Yeah, just a final word, like the communication between the Android tablet and the desktop is by using like a regular wireless network. So this is our user interface. Here XYZ is used to move the breast, and so as you can see, we have a fiducial marker as the background. We placed the breast relative to the marker. With the help of this XYZ, we can move it like up and down, left and right, front and back. And also we can choose what anatomical plane the breast is going against, and then we can choose an angle. After clicking angle button, like the breast will be reconfigured for the corresponding shape. And also we have a demo here.
Okay, so this is the starting breast, and I change.
So now I am moving to a different angle. After clicking the angle button, you can see the breast deforms. And now I'm changing to a different angle. So now I choose a different anatomical plane. This is a different angle. So now let's just review one more time of the contributions. So we did a parametric study to learn how a breast material structure and patient's position affect breast deformation. We used patient-specific data, and we put effort into preserving the shape of different parts of the breast, including the shape of the tumor. We built neural networks to speed up the breast deformation simulation. We extend the previous work by adding neural networks to learn the FDA and validate by comparing neural network results with MR scans. And we also developed an AR platform to visualize the breast deformation. As a few discussions and future work, we want to test our simulation in a clinical room. And we can add more operations such as palpation. We can explore other AR platforms, for example, HoloLens. And we might also use a gyroscope to find angles like in real time to predict the breast deformation. And this is very helpful, like in assisting breast biopsy in real time. Here are the references. And thanks, yeah, that's pretty much the end of this talk. And I think I'm right in time.
Okay, thank you, Kuo. So we will open up for questions, and I would first ask the audience if you have any questions. And after you are done, I will also have some general questions that the committee members may have. Following that, we move to the breakout rooms and have committee members ask more questions to the candidate in a private setting. So the floor is open. Feel free to ask Kuo any questions you may have. Go ahead, Yong.
Yeah, thank you for your interesting talk. And yeah, I really enjoyed your presentation. I have one question regarding the material property. So, I'm from more conventional FEA person who just first define the material property and do the FEA simulation. However, it seems that the material property itself is quite nonlinear and very specific to each patient. So I'm just curious how the material property can be determined for the simulation for patient-specific models.
Yeah, so for that part, we just get those values from like other relevant research papers. We didn't really test the material because it seems that's like a different project itself. Like there are quite many papers, they specifically just test that for a few years and they got different publications. Yeah, just for us, it's a little hard to,
Yeah.
that's because we have to find a patient and we have to extract, like do some biopsies to get the data sometimes. A lot of people, like they just use pigs to test.
Yeah, thank you.
Any other questions? If not, I will ask everyone to stay back here in this common room, and I will transfer the committee members and Kuo to the breakout room to see if there is any other questions that regarding the thesis or anything else. So please look for an invitation. Once I do that, please switch to the breakout room. Oh, sorry. Put it back. Are you assigning, Kuo?
Yeah, I am trying to.
Can you do that again, Arif?
Yeah, I can assign you, but I'm not able to assign myself, I guess.
Oh, no, actually, you can actually, if you're on the very top of your name, you will see a button.
Oh.
Okay.
Yeah, you can click on the option called breakout room and
On the top of that, you'll see move, and you can move yourself.
yeah.
Well, breakout. So I moved you, but I can't see my name.
For you, there should be an option called join.
Sorry, where is it? Where?
Below you see a block, right, called breakout room.
Yeah, yeah, I can see that, but my name is not there. Like, yeah, I think Dr. Kesh can see my name. I
Move
can't.
to.
Yeah, so breakout room, I can't see my name on that list.
You cannot see in the move list, but there should be an option called join. No. Or probably for the time being, you can make. Or not me.
Oh yeah, I can make you as the co-host, and you can.
No, actually, I'm on mobile, so that won't work. So I think they have come back.
That's right. Wait. Oh,
Cool. Let's do this again. Okay. I want you to come to the breakout room too, right? So go to breakout room.
okay.
And open room to all. Then, are you having problem assigning yourself?
Yeah, I'm not able to assign myself.
There is a way to do it. Actually, if you look at the very top of where you assign, you should see for yourself also, assign yourself. Otherwise, you know what? I will ask everyone else to just leave. Okay.
Okay.
And join a little later if you want in 10 minutes, or I'll thank you all and for attending, and just have the committee members and Kuo, you stay back. Okay.
Sure.
Let me be fasting. Okay. So if you are not a committee member, please drop off.
Yeah, I think everyone dropped off.
Yeah.
Oh, Harris is.
Harris and Srikar, you got to drop off too. I can force them to.
I can remove them.
Yeah. Okay. Excellent.
I hope my talk is not that boring.
No, it's good. So maybe I can start with a few questions. The comparison, so it's great. I like seeing the validation and seeing the comparison to the measured displacements. And I think that really adds a lot to what you have. Help us understand a little bit about the error that you measured in that displacement though too. So 3 millimeters, and as you said, that's in line with what other people are predicting. And I guess maybe you have an image here to help, but with 3 millimeters as a tumor error, how much does the tumor move with the 50 degrees? So we get a sense of maybe like how much percent this error is in displacement. Maybe you have the 50-degree image. Maybe you could talk about how much displacement that is.
So this specific part, yeah, it is at 50. Yeah, that is a good question. I don't think I actually have that specific number.
It could be from
Brad,
the
could you
neural
repeat?
network too.
Could you repeat that number again, one more time, question again, Brad?
Yeah. So just wondering, so the error between the predicted and displacement for is 3.65 millimeters. I'm just wondering how much the tumor moves with a 50-degree change in position.
The physical movement.
Because it presumably, and I don't suspect this is the case, but presumably it could actually be a very small displacement. If it was close to the point of rotation, then it could be a relatively small displacement. But yeah, so I just don't know what to make of the 3.65 millimeters to know how much of the displacement from that position, from that postural change, was compensated effectively by the neural network. And that's kind of the point of a validation step, is to show that it did accurately predict the displacement. So, and comparing to another paper where they compared to MRI may not be all that reasonable, because we don't understand what the conditions were from that other paper too, and what 2 millimeters might mean. It might mean something different, than ours. So
yeah, I feel that's a very good suggestion. I actually, so when I compare this, I don't recall I have a number, an exact number of it. It's probably in the code. So the reason I compare with this one is that using the same breast model from the same company, it's exactly the same model. It's just, when they manufacture, there's probably some variations.
Yeah.
Yeah, and also they collect from different angles, and they collect like a 45-degree angle, and that like their area is also very close, and they collect from different angles as well. They collect, so that's why I compare with them. I found the number is actually pretty close. Yeah, that's why like I kind of on this part I did not really go into very depth of like the percentage of that, but I think that's a very, very good question.
So it's the same company who made the Phantom.
Yeah, it's from this exact paper. Yeah, I actually compare with their result, and yeah, I just didn't.
So one of the things to think about, Kuo, is since you did the Phantom study, right? And I've seen the Phantom. deforming, the deformation is significantly different. It's like 10, 20 millimeter deformation in the breast when you move from 0 to 50. Visually, right? You can see a lot of deformation, right? But I don't know how much actually tumor is moving inside, to answer to Brad's question. Whether they move 10 mm and the error is 2 millimeter, or did you move 20 mm and the error is 2 millimeter, right? That is the question, right, Brad?
Yeah.
Yeah, that's the question. Yeah. It's
Yeah.
nice to hear that the deformation is large. And that, you know, visible, and then 2.69 is a small number compared to that, then that's great.
Yeah, this is a pretty small number.
Yeah, but if you, is there some way to actually for you to forget the physical part, just in the FEM part, since you have that simulation, can you pull up for any one of the tumors, what is the estimated total deformation, not the error, but the total deformation? Because you're anyway showing that in your color map, right? So it is computing the deformation, right? So you can quantify that as well, right, from that.
So,
Is that what you're showing here? I can't.
well, this is not for tumor, because I thought tumor would be a little easier, because surface point, we have so many surface points. We need to estimate the deformation. Tumor is only 1 point. So that's why, like, why collect, this is not for that specific phantom. This is for part 1, where we have those patient specific data. And I collected, like, for the surface of the breast, the percentage of node that has so much of deformation. For example, with 0.1 millimeter, there's like 50%. And if you go up to 4.5 millimeter, there's like less than like 10%. And also, if you, for large deformation, it can go up to like 14 millimeter. And you can see like the distribution of the displacements of all of those points. Most of the points for the surface, they don't move that much. And some of them, they're moving larger than the others. And you can get a sense of the distribution of the error. But for the tumor of this, I didn't really collect like that much of data to study. But you can see like it's more than 10 millimeters if the deformation is large. And even though it's small, it's between 4 and 5. So
Yeah, so it's 50 degrees, a large deformation. Is that?
In your picture that you are drawn from FEM, forget the MRI. Let's take FEM, for example, right? You have the picture of various postures, right? In that 50 degree, you have something close to 50 degrees in that image.
So
right?
what I remember, 50 degree is, it's somewhere here. That's what I remember. Yeah, so this is the 50 degree, and you can see compared to like 25 degree, 50 degrees is more.
Yeah, that looks.
I mean,
you can see significant move, and your error matching is pretty good match, right? Because if every point.
Yeah, so that error is, they call it nodal displacement error. We need to use an algorithm to find the corresponding points first, and then calculate the error between that. That's like a standard across all different research papers. That's just how I calculate the error. Yeah, but thanks for that. I feel that's very important.
From your existing computation, can you pull up some information? But for MRI, it'll be almost impossible for you to do, right? Because do you have an MRI for a zero degree position at all?
Oh, that one I don't have, but yeah, that's actually a tricky part, because you wouldn't have a 0 degree of breast. So I actually did a 2-step when I simulate. For example, when I collect the data from 25 degree, I want to find 50 degree. I have to do a first step of pushing up, like gravity, and then simulate the 25 degree, and then I minimize the error. So it's a 2-step process of that FEA. Yeah, but the center of the breast should be Yeah, since I have the tumor, I should be able to find the center of the tumor. And so that center of the tumor, like tumor is not, it doesn't look that uniform. So, I mean, it will be a little, if you look at this MRI, I have to manually segment the breast myself. I have to tell each image, like this area is the breast. And after that, it will construct a breast or a tumor. For the tumor, for the breast, it's easy because this outer surface is very smooth, but this one, it will be affected by myself why I color this this breast. Oh, sorry, this tumor. So yeah, I mean, there are some variations over there. Yeah, but I mean, the tumor is there. I should be able to find the center of the tumor and the exact displacement of it.
Okay. Any questions or suggestions?
Okay, maybe I can ask a question. So
Yes.
all this information is a function of the gravity load, right? The posture and the loading is gravity, which can be related back to density and density of tumor being higher and therefore causing some relative deformation in the elastic domain. So inside is a denser material, and because of that, there'll be relative deformation for different postures. So my question is, the figures that you show, they are highly anisotropic from all points of views.
Like the
very first picture, very first picture that you show the structure, it has muscle, it has ducts and all that. So the suggestion, it's more like a suggestion. I think the first step always needs to be something that we understand fairly well. I've taken Neo-Hookean material, homogeneous, isotropic, all those features are built in. So it means that any deformation and the loading is which is uniformly acting at all points in the domain, including the stiffer inclusion inside. So loading is uniform and the material model is also uniform, right? So
that's for the second part. That's for the breast phantom model we purchased.
Yeah, for that. And I think the objective of this study is deformation, but also, you said in your third slide or fourth slide that you want to predict patient's tumor location because of the different deformations. So I think the eventual objective is to be able to model the tumor and from the deformations, find the location of the tumor. That will be of clinical relevance. So my question then is, a good thing for you is that the loading is uniform over the domain, but unless you account for some kind of anisotropy in the material or relative stiffness in one direction versus the other, how confident you would be in terms of the numbers that you get and justifying its clinical relevance?
Like with the error I get and the
it's good to have error estimation, but there is all these features are also coming into play. I'm not that worried about whether the tumor is smooth or not, because it's one inclusion inside the other inclusion, and by and large, its relative motion is proportional to its density. So if your surface is smooth or not smooth, it is not going to make that much effect because the two materials at the interface, they are not moving relative to each other.
Well,
if the general mass is there, then that is accounted for. But the other question is that tumor, one can assume it to be homogeneous isotropic mass inside, but it is residing inside another domain which has directionality, right? Because of muscles and all those constructs.
Right. Yeah. I mean, that can make it more complicated. I mean, if you take those like contexts into account. And the tumor itself, I mean, usually it's small, and you know, they're like spreading everywhere. But so it's very hard to accurately like describe the property of the tumor. Like,
Okay,
yeah.
so let me say, let me ask it another way. Now that you have done this work, in what context you can use it in a clinical trial?
I see. Right.
How would you
So
use it?
usually when patient, like I think I said somewhere, but again, yeah. So usually when the patient take MRIs, like they just put it, we put them in like a giant MRI machine, and after they're done, after a few days, they can come back, and then they will use like an ultrasound thing to actually see the tumor. And if they have to get a test, they will have a biopsy. And you know, at that point, that shape or their position is not going to be exactly the same, like compared to where they were when they were taking the MRIs.
Mhm.
And even a little bit of change of the position might cause a shift of the tumor. And if they, for example, when they take the biopsy, if the needle is not inserting into a correct place, that part of the sample is not useful. So that's why like we want to see whether like if we can predict where the tumor is, like based on the original MRI, then when they take the biopsy, at least they can get a sense of where it might be, and then they can adjust their needle position.
Okay. All right.
Thanks for the question.
I mean, if doctors can constantly see, like, for example, go for a tablet, but HoloLens, you wear on the head, it's a see-through glass, right? You can see through it. If you can constantly, as the patient is moving, if you can sort of see a hidden graphics of the tumor also move, that actually will be very good for having a much more reliable, even for mastectomy, partial mastectomy, where they only remove part of the tumor, part of the breast. Having an idea where the tumor is with respect to the MRI is a challenge that Mayo gave us, right?
I see.
He said, most of the time we end up removing too much of the breast because we don't know. If we had the ghost eye can see inside the breast, because we know the ground truth is available through MRI, right? Except it's not available. The patient, once they lie down on the bed and they in a posture, the breast completely has moved, right? So, I mean, it's a long way from there, but this is the direction that it's trying to go. His animation, which he does in real time, that is actually pretty good. I don't think anybody has done that because, because FEM doesn't work at that level, but neural network does allow you to do something.
Yeah. And I mean, we can collect the angle of the patient in real time, like using the gyroscope. You pretty much can see it moving like in real time.
Exactly. I mean, if you can estimate the posture at the time when the scan was done mathematically, and then compare the posture of the patient, right, using some stereotactic techniques, then you could also estimate how much posture with respect to the earlier motion is. A lot of computing, but in the brain area, they do a lot of stereotactic computing, right? Simply because they use some amount of these kind of data for location of the tumor in the brain, but in the head can be locked with screw, right? And you can get a fairly good fiduciary markers and things like that. Or you do intraoperative MRI in brain, right? But in breast, there is nothing like that. There's no intraoperative MRI. There is no way to hold the breast in a position. There are some ultrasound machine that even GE have invented, which actually completely holds the breast using plastic, armors, but they have never been successful in a clinic because they don't like using that highly cumbersome system to find one tumor. So there are a bunch of FDA approved things which I've never seen inside a hospital.
Okay.
Ours.
My question is, first of all, I think this is an important first step. I'm fine with simplifications and all, but let me just try something a little different, right? So you're predicting the shape deformation by appropriate tools. Now, supposing you had a control point grid, right, which will be basically like a graph paper like thing, highly precise, that is projected onto the breast surface as even if the patient is moved, deformed, whatever. And then if I had two cameras that's going to look at these things, I can predict the 3D shape by looking at the by the two cameras. So it's like overlaying a grid on top, and then there would be deformations on the grid shape, and from that deformation, I can infer the shape, right? So I mean, this is not what you're done.
Yeah.
So now I can predict what should have been the orientation. Your neural network, or whatever technique, is predicting something else. And if there are some errors in there, so I'm just thinking about a slightly different scheme here, which can improve accuracy just in terms of shape deformations. And in that particular, so on the surface of a HoloLens kind of a thing, this would be literally it's basically a graph paper that has been kind of projected onto this particular curvilinear surface with a X marks the spot icon, which basically says, I mean, this would be where I think this would grow legs and run in an application space. But I mean, as you were talking, instead of HoloLens, I would go with a control point grid being projected on top of the curved surface, and not just for breasts. We can do this for other applications as well. But in terms of shape, I'm pretty impressed with the accuracy. Now, there's a bigger issue of, did the tumor relocate? That's a different story. Just talking about the way how you have predicted the shape of this object as it would move, right? So that's pretty nice. Anyway, that's it. That's a general comment, but other than that, I don't have any question per se.
Thank you.
Very good suggestion, RS. When I was talking about stereotactic techniques, this is exactly what I meant.
Okay.
You see, having some stereotactic model. I mean, these are all prime for deep learning and things like that. You know, AI-based system to. I think just the imaging part of that could be the missing link between the computation and merging.
Right. I mean, so we can have an LCD kind of a display. I mean, again, let's just talk about just generic stuff, right? So if there's an overlay of a graph paper, the grid spacing is quite far apart. You recognize regions where your prediction is not super accurate, quote unquote. There you can make finer grids, and the camera is going to pick. I mean, but nowadays, even with anyway, so that's very the thought just crossed my head as you were presenting this, but good job. Anyways, that's all. That's it.
I think we have phantoms and all that. RS, we should at some point think of writing a proposal around that.
And we just need a very high quality projection device.
With nowadays with this LED things that people are using for, even for SLAM control and all that, the robots are using those dot grid LED. We can
exactly.
get
And they're building things, right? So these are actually lasers
those
that
things
are rastering through very quickly, but that might be dangerous to use in a hospital.
You know, the interesting thing is that Air Force and others already use that for getting high resolution terrain in Mars and all that. This is exactly what they do. You know, they scan and get very high resolution, you know, sub-millimeter or a millimeter resolution terrain.
And we don't need a complete permanent overlay. You just need a single scan. And then at that point, maybe you can transfer it onto a HoloLens or something. Anyway, it doesn't matter. Good. Very good. Got me excited. That's all.
Yeah, that's good news, RS. We can't excite you easily that often. So. Good. Any last thoughts? Otherwise, I will ask Kuo to I think, am I a host? Can you make me a host before you?
Yeah, you are a co-host, so I can't stop sharing.
Okay, do one thing, make me the host, okay?
Oh,
And then I will text you, only then you come back, okay?
okay, well,
Just make me a host.
yeah, I mean, yeah, you are a host. Like,
No, not co-host, host.
um,
You can change me to host.
okay.
I think, okay, I'm a co-host right now, more.
Yeah, change host. Yeah, I already changed you as the host, and I
Okay,
can.
now it shows me a host. Now you can drop off and I'll text you back, okay?
Okay, all right.
Okay, just hang around, don't go anywhere far.
Okay, sure.
Okay, thank you.
All right. See ya.
Okay. Any thoughts, any corrections or things that you want him to focus on?
I think I'm happy with it, and this is a good step. And I think your subsequent students can build on top of that and take it forward. And
Yeah.
the thing that I would suggest is more sophisticated material models.
Yeah.
Have some kind of directionality. And one thing I would say that there are enough models that have been developed for plastics reinforced with directional fibers. And I think those models, so you take those models and you don't use the coefficients of very stiff material, you use very relaxed coefficients. So one needs to take a look at the two things. One is how far those models, because they have directionality built into them,
Yeah.
how far those models can, the parameters can be changed, and that model will still be compliant with the second law of thermodynamics, one thing. So this is going to be more a fundamental study. Second thing is, when does that model become mathematically unstable? There are, these are functions. So the functions are function a certain range of parameters beyond which they go very high or very low and all that. So in between, they are doing the thing that we want. So two things, how far can we move them so that they represent a soft enough of material, incompressible, soft enough of material. Secondly, we are not violating the second law of thermodynamics. These are going to be mathematical studies. Once these are done, then those models can be taken because they have directionality and people have developed them in material science domains. We take some of those models and use in civil engineering and aerospace engineering for load carrying members with reinforcing fibers. And those reinforcing fibers can now be used for the different structures inside the the breast. And the thing is that it has to be done in a spherical domain. So big picture kind of thing. So it's a mathematical problem. Once this is done, then next step would be that now that we have a model which is validated on idealized materials, now let's say we look at a control model, and it could be a mannequin model, where you have the properties and you can take measurements, different angles, and calibrate your model how accurately it comes out to be. Yeah. That done, then you can go ahead into the clinical. I mean, that is how I would say. So you still have,
these
I think,
materials
2 steps.
you're talking about, they can be like viscoelastic materials or?
Yeah, viscoelastic materials, yeah. But polymer industry has done it a lot.
Okay.
A lot of it. And actually in polymer processing, what they do is their fibers are considered to be inert, very stiff, and the polymer or resin is poured in there. It chemically cures and solidifies. So what in those constitutive models, the coefficients, the mechanical coefficients, they increase. For example, if the material was very soft and becomes hard, then your modulus of elasticity has to grow up as a function of curing. Okay. So that those constitutive models to begin with can take a range of parameters, not just one parameter, like in Newtonian, Monin-Rivlin, we pick Poisson ratio and this and that. And so in those models, there's an evolution. Those models can be taken and first tuned to this class of materials. Yeah. These models be tested on, you can say, molded with controlled shape of the inclusion and the density of inclusion. So you know exactly The good thing about the whole thing is that the force that is deforming, which is the acceleration due to gravity, is constant. It's not going to change. And one can always take advantage of something which will never change in your lab or in your clinical test. That is a constant. Gravity load is a constant. So it means with respect to that, you can calibrate things.
It's interesting. I mean, next, I think if we can write for a grant, right, R21 or something like that, we can get a really good PhD student from your lab to, work with the more computational and visualization side, and clinical side that, I do. Can put together a team like that. I think they can hit it. I think it's not been addressed, these areas.
Yeah, and people, and I've seen people using material models and not realizing that those material models are invalid beyond the range that they are actually ending up using. I stop students all the time in different departments when I serve there, that you are using it fine. It looks like pictures you're getting are fine. Go and check. You're violating second law of thermodynamics. If you really run the simulations long enough, they'll blow up.
Yeah, it's a very good point. People don't think about it, especially students, right? I don't know, Brad, did you attend this Mount Sinai neurosurgeon's talk last
No,
Thursday?
I missed it. Yep.
So he was talking about brain tumor, they're segmenting, all these things they're doing, right? And then when the patient comes and dies, the patient's brain is all over the place. Right. So they have no computational model, nothing. Is all highly segmented graphical model. They say, oh, we have solved the problem and all that. Finally, I asked them, how do you solve the problem? Oh, we look at it and with the touch screen, with the finger, we move till it merges them again. I said, oh, okay. So, and he said, oh, that's what you guys do. Maybe you can help us in modeling. So I have a lot of work in brain deformation because more fluid thing, but it's clinically nobody uses all this stuff because they don't have any tools like that.
Yep.
Brain Lab, Brad, do you know about the software called Brain Lab? It's a segmentation software. Right?
Yeah.
Do you have it, Lab? No.
No, we use other things for segmentation.
Okay.
Yeah. So, yep. Yeah, we also measure mechanical properties of the brain if you want to, or other tissues with MRI too.
So this Mount Sinai guy, at some point I want to connect with him again. Right? Because he's very interested. His daughter is a first-year student in CIMed.
All right.
And he's the head of neurosurgery in Mount Sinai, entire program, big shot. So he was very interested in working with our engineering. So at some point I want to put together a team to talk to him.
That sounds good.
Yeah, okay. Well, thank you all. I'm going to ask Bo to come back. And I sent all of you the forms. What you need to do is just sign and send it back to Lauren. Right, Aris?
Yeah, I'll just do it now.
Yeah. And then
Do we all have to sign the same one? Do we need to do it in order?
No, you can separately sign it. Separately.
She'll take it.
She will take care of it. Yeah. I think at one point in time, maybe all you do is send an email, right? I agree or something. But or I think she wants it signed. I think Okay. Let me see if I have Go's link here. Cool. Okay. I'll take a photo with him so that. So I think, Brad, you win in terms of the background. Okay. You look like a peacock now.
Yeah,
I know. Sorry. It's not.
It took me a while to figure out that it was
brain
not
fiber
peacock.
tracks. Yeah.
Do you know peacock is India's national bird?
Oh, really?
Oh, is that?
Okay.
Oh, yeah.
So it's not something to be ashamed of to look like a peacock then.
Oh no,
Okay.
you'll be a big hit in India if you wear that.
Okay. All right.
Is it the white peacock or the green color, the
Green ones.
Green.
Right, the green ones. Yeah. I don't know why it is, but it is. Yeah. I hope you got my message. I hope you let me call him. I hope we did not started celebrating early. It's not picking the board.
So we have 2 documents to sign, looks like.
I believe so. There are 3 in that. One is instruction. It's a letter to the charge to the committee. The other 2 are the forms. I told him not to go too far. Unless he has another phone number. Let me just check. Maybe it's another phone number. Because my last text to him. Okay, maybe I'll email him. It's likely he may have changed his phone. I don't know.
You want us to check pass with no revisions? Or should we take pass with revisions and you'll check them?
Yeah, I will check one more time.
Okay.
But if you have any specific revision, you should either email me and saying this is what,
Yeah.
so that I can check with that when I finish the revisions.
Yeah.
Or you
I'm
say
just
part-
curious about the displacement because
Yeah.
the plot, the figures in part 1 showed about 4.5 millimeters of displacement for the tumor. And then his error message showed about 4 millimeters of error in estimated displacement, which I'm sure is not the case for the phantom in part 2.
No, no.
But it would have been nice to kind of have that closed, but yeah.
Yeah,
Yeah.
and also the surface errors are different than what you were showing was the breast surface errors.
Yeah,
right?
yeah, yeah.
And high displacement maximum was 14, but inside, right, it goes
It's-
straight.
yeah.
Outside shape goes, but inside,
Yeah. it was a
actually
little
we
bit
don't know,
unusual.
but yeah,
Yeah,
it might have been good if he had taken an MRI in 2 positions and just,
oh yeah,
see.
and just look at the difference, yeah.
Yeah, I
Yeah.
know he had a lot of trouble just aligning and getting he spent like weeks together, and your postdoc or whoever really helped him a lot. Thank you. Cool. Welcome back. So congratulations, Dr.
Thanks.
Kuo.
Thank you so
Um,
much for all the help.
I want to take a quick photo before one of the suggestion
Okay.
Professor Certain has. So.
Let me then sit up.
Well, I actually changed my clothes.
I told you not to go too far. Okay, that's fine. Kuo. You still look good.
Thanks.
Okay, smile. Okay. So Dr. Sutton was saying that see if you can go back and check from your computation model
Mhm.
whether you can measure how much, take any one tumor and see what measurement you're getting. You don't have to do MRI, it's too late, but in the FEM model, right?
Mhm.
Get an estimate. So you can compare your
Uh-huh.
actual movement with the error that you're predicting.
Yeah.
Okay, so if the movement is a lot and error is 1 mm, it's really good. If your movement is 3 mm and your error is 1 mm, then your measurement is still pretty fuzzy, right?
Yeah, that's a very good suggestion.
So if you can do that and show it to me, I will share it with everybody. That's the only last thing. I mean, I don't know how many days you have to finish this, but I suppose you have some free time in your hand to see how you can. It may be good for your paper as well, the second paper that we are working.
Yeah. So the error between the neural network and the FEA is very small, but I guess between the FEA with the tumor with the actual MRI is probably a little large. That's my feeling, but
Yeah.
Yeah, large is good. I just, what is the total displacement and what fraction of that total displacement was compensated for by the prediction and so I think it's just you show in part 1, you show errors on the order of about 4.5 millimeters for the tumor. And then your error in the MRI section in part 2, which are 2 completely different models, 2 completely different materials, you show your errors about 4. Right, so 3.6 or something. So I think all it is just a matter of finding out how far it moved in the in the 50-degree rotation, just so that 3.6 is, you know, is a fraction of the total distance moved, right?
Yeah.
So, and it's okay if it's a big fraction of it too. It's just, it's really hard to interpret 3.6 as anything valid. We have no idea how much the tumor moved in the first place.
Yeah, so I was actually confused by the paper they've published. I just compare all those numbers with their paper. Yeah, so, but my feeling is that it is probably a large portion,
Yeah.
but I'm not sure. The only thing is, like when we describe the surface of the breast, you know, there are many points. So the average area becomes small because there are so many
Yeah.
points. And when we describe the center of the tumor, you see like in the tetrahedral mesh, like we have to actually get into the inside of the breast, not the surface of the breast. Like, so
Yeah.
when FDA is calculating inside of that, it might not be that accurate.
Yeah. All these methods have drawbacks for sure. I
Yeah.
think it's just a matter of providing
Yeah,
the context to interpret. Yeah. And,
Right.
and the performance looks excellent. So, yeah.
thank you so much for the help. The MRIs, you know, they were so helpful.
Yeah.
Yeah, they were very helpful. Thank you very much.
That's great.
Right. Okay, wonderful. So, Kuo, we will sign off on that, but you and I can have a little bit more conversation about the absolute displacement thing, right? Let's see where
Yeah.
we can add some more light to it.
Uh-huh.
If we
Yeah.
can then include that in your thesis, right? Otherwise, I will just scan through it one more time and then I will approve it.
Okay, sure.
Okay. Very good. Excellent.
Great. Congratulations.
All
Thank
right.
you so much for coming.
Thank you all.
Bye.
Take care.
Bye-bye.
Thank you.
Kuo, can you just wait for 2 more minutes? I'll
Oh,
just
yeah.
talk to you. before-
Yeah, yeah, sure.
Okay, very good. Just a smile. I'll take one more photo, okay?
Okay, sure.
Yeah, I'll take it.
Should I change my clothes?
No, your head is, yeah, if you want to change to a shirt or something, I'll wait.
Like what, 1 minute?
Yeah,
Let me.
I'll wait. No worries.
I guess for a photo, this is,
Yeah, I agree. Look much better that way.
yeah.
Okay. Very good. Smile. Okay. I think I'll send you the photo, okay?
Yeah, thank you so much for the help, Dr. Cash.
Okay. No, congratulations. It's a long trip, I know.
Yeah,
So what I want to do is when you come back to campus one day, maybe you can come on a Saturday or something, right? I want to get most of your code and executables and things like that on a computer so I can show it to other people or use it for writing proposal or something like that,
yeah,
right?
sure.
That'd be really helpful for us, is to have a version of it running here in the computer, right? And also the animation that you do on your thing and the tablet, all of this thing, if you can like pass it on to new Srikar, who's our new postdoc, or to Manusha, or to or Harris or somebody, we can decide to put everything in a computer and have it so that somebody else, if they want to continue on this topic, they don't have to start from scratch.
Yeah, sure.
Okay.
Yeah, I can come probably like during weekend or.
Yeah, if you can come on a weekend if you're busy with work and all that.
Yeah.
Okay.
Hey, sorry, can we take one more? I guess I didn't turn on the light. I'm sorry.
All right, sure. Go ahead. Put on the light. Yeah.
You know, I said. Yeah, sorry.
Not much of a difference. The previous photo was pretty good.
That's
I'll take it. Okay.
All right. Thank you.
All right. Wonderful. Well done. Cool.
Thanks. Yeah, I'll let you know about the accuracy stuff. I'll spend some time.
Yeah, actual displacement, more than accuracy, the actual
Oh,
displacement,
yeah, the actual displacement. Right.
absolute displacement. Okay.
Yeah.
Okay. Thank you.
Thank you, Dr.
Talk to you
Cash.
soon. Okay. Bye.
I'll see you.